to interrupt, but we can't. Sorry to interrupt, but we can't hear the sound and the slides.
Hi, is there? No? Hey, no. Yes or no? Oh, very interesting. Okay. So I'm sorry about that. So first, I'm sorry about that. First is we cancel presentation. Second, exam will be take home during the weekend of the last week. Third, we have I have think about the makeup class is October 29th and December 4th, which optional material will be recorded as well. Fourth is today we will consider uncertainty, and sorry about that. So uncertainty, sorry, I just 1 minute, okay. So the way we do uncertainty is very classical and same as what we learn probability. So we have complete knowledge of what might happen, okay, but we don't know which one. So, but the probability is objective, okay. So there's no surprise why such thing can come out. We only surprised at why this come out rather than another one, okay, and that is the model. And the simple case is simple gamble. Simple gamble simply means that we would describe the uncertainty by telling us what are the possible outcome and what the probability. And we focus on the case where n is finite because of that. When you go to infinity, things become very different. But especially when we prove the axioms. Okay, later you will see why we need this finite assumption. And but that being said, the modern theory actually extends to infinite outcome with some technical assumption here and there. But we'll not go to that because it's not crucial. And I want to say the focus of the modeling, the way we model the uncertainty, of course, is not only one way, there are many ways to do it, but the way we do it is the most classical one. And as I said, that would be the one that I've seen in the most of the papers, okay? And here is the compound lottery. Compound lottery is saying about your lottery over lottery, okay? Maybe I just draw a picture that probably would help a little bit. So the idea of this is, right, is simple lottery can be represented by, well, okay, I remember the pen is useless. So simple lottery is like this, right? A1, A2, sorry for my writing because writing with the mouse is not easy. So you can see simple lottery is, you think the future is a tree, right? There's n outcome here, right? Each outcome has probability there, okay? That's no problem. And the compound lottery means the following, right? Maybe I use another color. So you will be talking about, first, you have a probability, okay? Maybe K, all right? And will be gamble 1, gamble 2, up to gamble K, right? And each gamble maybe lead to some lottery, and maybe some lottery, okay? And note that need not be equal number, right? So the first one have 3 outcomes, the second one have 2 outcomes, the third one have 4 outcomes, okay? So that would be the idea how you are going to represent this in the real world. You can think game tree is the way. I mean, this is standard way you learn probability, right? You learn game tree. So this is exactly the probability tree. So this is a probability tree to represent uncertainty. As I said, this is not the only way to do it, and but this is still the most dominant way to do it. So we just follow that. Okay. And for those who do marketing, maybe we do behavioral research, they will argue that it's not the only way. I mean, they will do many other ways. But as for me and for most applications, you don't need to worry about that. So the example like this, okay? So it's combining toss a coin or a die. So here is the very simple. Just toss a coin. If head, you win. You tail, you lose dollar. And the amount you win or lose depends on roll a die. I roll a 4-face die. Okay. So it will be like this: a compound gamble. Half you win, half you lose. The amount of win and lose depend on whether say the die is a fair die. So if 1/4 of you win 1, 2, 3, 4. Okay. So that is the way, right? So if you try to draw that, it'll be something like this, right? You decide 1/2 and 1/2, right? And after that, you will give 1, 2, 3, 4, right? If this is head, right? And this is tail, then you also have 1, 2, 3, 4, but it's -1, -2, -3, and -4. Okay, so that is the way to represent. Okay, is that clear what the compound lottery is? Okay, and now if that is okay, then we go back to the slide. So we will define, okay, because of the fact that there are finite number of outcomes, right, and then they're fixed, so we can simply hold the set of outcome constant without refer to it, okay? So we call outcomes, it's just set of outcomes, and we'll call lottery, okay, instead of gamble, just my notation, because some book we use very different way, so I just make a distinction. It's not universal, but I think there's an easier one. Lottery, we just probability, okay? When we write probability, a vector, you imply this, okay? I just don't need to do it. In this example, right, I have 1, 2, 3, I have actually, we consider 8 outcome here, right? Because finite, I can always do that, right? I can just, even though there are, you may consider this outcome and this outcome will be same in terms of rolling a die, but we will consider distinguish 8 possible scenario in this case, okay? And compound lottery is same lottery over probabilities, right? Lottery over lottery, okay? So, and this example, right? If I have a roll a fair die, right, over the 6 outcome, right, I can represent by P is equal to 1/6, okay? And I can have 2 dies. One is fair, one is unfair, okay? A fair die is P1, right? And the fair die is P2, right? One only happen to be, there's no way you get 4, 5, 6, right? So that would be the way, okay? Or are you, okay? Is that clear? So, and now we will talk about one of the theory, the many theory, but there's one of theory which I said is dominant use is to model how people make choice under uncertainty. Okay, there are many theory. So the one is you learn in undergrad. It's called the expected utility theory, which I will define later. So, but the main thing we want to talk about is to give you the foundation why expected utility is right. I mean, probably many of you might know expected utility invented by John von Neumann, one of the genius in the last century, who also invent game theory. Okay, so that would be the way we do. Okay, so we give the foundation for expected utility. Okay, later you will see what do you mean by that, but let's give the axiom. Briefly speaking, expected utility is saying that utility over a lottery is based on look at each certain outcome, you have utility, and you look at the weighted sum of it based on probability, okay, which we will define carefully later. But if you want, that would be go to the last slide first. It's just saying that utility over a gamble or lottery, right? It's just expected utility is probability multiplied by each certain outcome, okay? So that is the foundation we want to give, okay? And I hope this you learn in undergrad already, but we will give the foundation for that, so don't worry about that. So that is the goal. One of the main goal of today is to give you foundation, give the proof. We'll do a proof. Sorry, we'll do a proof today. Probably there's only one proof we'll do today, is to give you an idea why this is true, okay? And so remember we have n outcome, okay? So we can focus on lottery, which is in the n-1 simplex. n-1 simplex is just saying the probability, it's just saying this. This is simply mean P1 plus P2, right? Up to Pn equal to 1, and Pi are between 0 to 1, right? I do this because you look at all the paper, they just mentioned this n-1 simplex. So, but nothing new, but just saying that the actual probability, there's nothing new. Okay, just saying that probability. Okay, and the first two axiom, I think, is not anything surprising to you, right? Because there's actually we assume that in the topic 1, right? We assume it's complete. We give you two lottery, you must say you like A over B or B over A or the same. Okay, you can say something. You cannot say it depends. So I think that's fine. Okay. The second one, of course, as I said, this is a little bit tricky, and actually there's a lot of paradox associated with that transitivity, which is requiring to say if A better than B, B better than C, and A better than C, right? P better than Q, Q better than R, and P better than R is some of consistency property, right? You don't go crazy. Usually, when we talk about behavioral economics or experimental economics, usually is people is they kind of if you tell them you make a choice that's not transitive, they know they will correct it. So it's basically kind of like people it's like about bias or mental capacity. If you tell them you do a wrong choice, they can correct it. It's not something like they would consistently aware. They don't aware they don't follow this axiom compared to other axiom. Okay. Okay. If they know it, they are able to do it that way. So this probably is not that strong. Okay. It's not a big problem with that. Okay. And some notation. Because with complete and transitivity, okay, and we can write this if there are P better than Q, Q better than P, then we'll say P equal to Q, right? And we can compare all outcomes from A1 to AN because it's finite. And we can also, with the loss of generality, we can rank them from 1 up to N. 1 is the best, N is the last, because we can do comparison. The reason is finite, right? Infinite is an issue. There's some issue there. And to simplify notation, if probably 1 is AI, just by AI, just to save space, okay? And this notation not invented by me, the book, so that's why I just put it there, okay? So the next one is continuity, and probably continuity is something that you remember, is something that in preference means, or in other cases, things doesn't change rapidly in the neighborhood, in the nearby area, right? Remember, we learned preference. When I say preference continuous means what? If X is strictly better than Y, okay? Something nearby X still strictly better than Y. Do you recall that? Okay? Same here, okay? If log 3X is strictly better than Y, or P better than Q, something nearby P should be better than something nearby Q. So that's continuity 2. Right? The meaning is if P better than Q, there exists some radius, okay, that in the neighborhood of P, which is P prime, neighborhood of Q, Q prime, P prime is still better than Q prime. Okay, so I think that's easy to understand because when you look at this is a Rubinstein definition. Because when you look at the definition of either 1 and 3, which is given by Maslow, Green, it's very difficult to understand. What do you mean by this preference is close? Not entirely clear, but I mean, 3 of them are equivalent. Anyway, you can look at Rubinstein textbook. He has a very careful proof for the 3 of them are equivalent. I'm not going to touch on that. The first one, I think first one also can be easily understood. It's not something that's too terrible. I mean, easy to understand as well. This is saying the following, okay? If I have, you can see I have 3 lottery, P, Q, R, and there's strict ordering, okay? There's a P better than Q, Q better than R, okay? And you can always find a mixture or mixing the best and the worst, okay? In some way that they're the same as Q, okay? And you can't do that, it's not continuous, right? There must be some way you can mix the best and the worst to make you equivalent to the middle one, okay? And you can easily see this is very helpful for proof, right? Because later you will see, when we do the proof, actually we will utilize this continuity property, is everything can be expressed by the best and the worst, okay? And later you will see this is crucial for the proof. Is that okay? So that is continuous, okay? Now, the next one is one of the weak axiom. We don't directly use it, but it's an implication. This is, I think it's rather trivial, okay? But it is interesting. You can take a look at the proof, but I'm not going to do that. But this is a very interesting proof. Interesting axiom first. So axiom is I have 2 outcomes, AI and AJ, okay? And suppose AI is strictly better than AJ, okay? And consider that, okay? Alpha better than beta, so alpha is bigger number, okay? So that means here, multiplicity means that if I give higher probability to a better outcome, so be better than the case I have lower probability for a better outcome. I think that is rather clear, right? I is better than J, okay? You have more likely to get I over J. So this is better, right? That means that I increase the probability that you get a better outcome. You should be better. It can't be other way around. Okay, I think that is rather normal. I mean, no one would disagree with that. Okay, of course, but we will not require stronger axiom than this one. Okay, much stronger. Which, of course, again, people always complain this kind of axiom. It's called independence. Okay, and this kind of axiom usually would have a lot of challenge from experiment. It said the following. Okay. I have 3 lottery, P, Q, and R. P is better than R, okay? And what I'm saying is, if P is better than R, right? P better than R, okay? Remember P better than R, okay? If I try to mix it with something redundant, somewhere Q can be better than P or R, Q can be anything, okay? Q can be anything, okay? I just mix it, doesn't change. Okay, so let me say the following. You like this over the other one. Okay, I tell you that, okay, let's do another lottery. Okay, such that in some probability you get the other one. Okay, you mean the same. Okay. Exactly. This is actually a lot of controversy of that always, because why it has to be whole, right? But this is what they think. Okay, and there's some issue with that is because people would think 0.999 is different from 1, right? You look at, I mean, for people who marketing, you know, right? And look at the price, they make $5 and $4.99 is different, right? So people actually, probability is not really that you continuous, right? A little bit slightly different. So here is like something when you maybe from 0.999 become, from probability 1 become 0.99 is actually different from that. So in that case, people things get changed. So that is the independence always fail in that scenario, right? Because something when you switch from probability 1 to probability 0.999 is slightly different, right? And there's a distinguish between that. Okay? But later I will mention that, I mean, what are the model that are trying to capture those ideas. But I think independence is axiom that in general, that's fine, right? Just like you prefer stock A over stock B, right? Stock P over stock R, say. Stock P gives you higher return than higher risk return trade-off than R, right? And then you told me, okay, let's include 20% of the bonds in your portfolio, right? And then probably you would think still you would prefer the same, right? Adding certain things shouldn't matter, right? If you prefer stock A over stock B, and I say, okay, why don't we add stock C to the two choices? You think the same, but probably do the same, right? You wouldn't think differently. You would think you would separate them in your mind, make it easier to think, right? You would value them. You would think them the same, right? Also, if and only if, right? So that means that I take out the common component, then you think the same, right? It's kind of reduction, right? Look at two portfolio, but look, you go to the restaurant, okay? And if you try to order menu or food, right? You may order some probability associated with the menu A, B, and C, right? And you may look at the first dish and second dish and third dish, right? You think separately, right? If you think separately, that's the case, right? But if you think I have vegetable and you have meat, you have soup, those kind of thing, then you think you already have salad, then you probably don't want a vegetable soup. You're related in somehow, in some sense, then probably not. Okay, so it is kind of like making easier, but whether this hold, it depends. But in general, that is the right way. Okay, and the last one is something that probably you might or might not agree. It's kind of again a reduction idea, right? Similar to the independence. Okay, it's saying that when you look at compound lottery, you don't actually care about how the lottery comes out. You only care about the outcome and the probability. Okay, you don't really care about you do many lottery and then end up this. You only look at the final probability. Okay, you don't really care about this outcome had this probability. This outcome had this probability. You really don't care. I really toss a coin. I really use computer to generate the outcome. I use very complicated process. So the process doesn't matter. Only care about the probability. Okay, rational, but actually people do not think in this way many times. Especially when we present a very complicated lottery, we will do some type of rule of thumb step by step. Especially talk about simplified probability, right? Because when you can imagine, when we have very complicated probability tree, right? Let me draw a picture, right? Let me look at here, right? We're very complicated probability tree, and down there's some probability 0.999 and 0.001, right? And 0.001 maybe you just say, okay, forget about it, right? And you think this is better, right? And that means that you are doing some simplification along the tree. Okay, it's not, but reduction require you to actually cannot do localized like this. Okay, you have to look at overall. Right? Even though the small probability maybe add up all the tree together, that can be very large. Right? You cannot simply skip, okay, tree by tree, but that's something like that. Okay. So what I want to say now, before I do that, is reduction like this. Okay, act like this. Suppose I have A1, A2. I have two lottery like this. Okay, P1 and P2, and I have lottery over lottery. So 0.3 of the time I get P1 and 0.7 of the time I get P2. So for reduction, it actually means that this lottery will be same as I just calculate what are the outcome I get. I get outcome 1, right? Which is 0.3 of 0.2 and 0.7 of 0.4, right? It's 0.34, and same for action 2. So reduction means I don't care about how it goes. I only care about what the probability I get for each one. Okay? And of course, that require you, or decision maker, can do the calculation, right? And can do exactly correct. Okay? There's no mistake. Okay? But of course, you know that's always not the case. But assume that the guy can do it without any problem, even though it's very complicated. Okay? Okay? You are not doing any kind of rule of thumb, but it's rational. Now we are talking about some proof. Okay? For this, I'm not going to prove. I think you can check it. This proof is very simple. I think I'll leave you for as exercise to prove it, or you can ask me during the break. It's very simple. Its independence imply monotonicity, which will be a simple proof. Okay, you can check it. It's just 3 different cases, and you can apply. I'm not going to go over that with you unless you want. Otherwise, I'm not going to talk about that. Okay, this is case actually direct proof. I'm not going to go about that, but those who want to do theory should check it out. Okay, I will spend the time to talk about this theorem. Okay, this is proved by von Neumann and his co-author Morgenstern. That's why they call von Neumann-Morgenstern utility function in the literature. They call. So basically, what he said is, suppose with all the axiom we have, right, complete transitive, continuous, independence and reduction. Okay, all the axiom. Okay, and as I said, the utility over lottery is weighted sum utility on outcomes. Okay, as we said like this, right? Utility over lottery will be just expected utility. Okay, there's no uncertainty anymore. What you do is you look at every possible outcome. Okay, this outcome uncertainty, right? Look at that, how you like that. Okay, and you weight based on the probability. Okay, and here before I mention a little bit further is you can imagine that probability you feel may not be linear, as I said, right? 0.999 may be different from 1, right? And also maybe 0.111, 0.001 and 0.001 may not be very different, right? And that's why a modern theory will call probability weighting. Here we will have, say, some omega or W function of P, nonlinear. Okay, I think probably know it's called the prospect theory, and they will. I think the probability function looks like this, if I remember correctly, something like this. The function looks like that. So this is 45-degree line there. This is P, and this is omega. Okay, and as I said, 0.999 is different from 1, right? 1 you go up a little, go down a little bit, right? Something like that. Okay, and nonlinear. Okay, but it's not the purpose of our talk, and but that would be the goal today. I mean, first half of the day is to prove this guy, but the proof is not complicated, so don't worry. It's similar to what we prove existence of utility. Very similar idea. By construction. Okay, the construction is again the best and the worst. It's a kind of idea. Okay. Now let's do the proof, and after the proof, the break. Okay. So the proof is not complicated. Okay. So what we do is to try to show you that there exists by construction. There exists of the way to rank this guy. Okay, for every lottery, I can express map to the utility. The higher utility, the more we prefer. That's the proof, right? Utility represent the preference. So we just try to construct how to tell you how to construct that. Okay, that's construction proof. That is the best proof, right? Because you tell them how you do the construction. Okay, the first case is trivial. Okay, if A1 is equal to AN, A1 is the best one, AN is the last one. If they're all the same, right? Which the case you should prove because this is for rigorous. If the same, so everything in the middle is the same, right? Because transitivity, right? And that means that by independence, any lottery is the same, right? Because you don't really care about the thing, right? Because you remember, independence means you add and add things away and subtract the same, right? So you can always do that, okay? You can add things, lottery over stuff, right? The same, right? Because every outcome same, lottery over them same, okay? And that means that you can set UA equal to 0, all outcome. So everything same, so expected here is same for everything, right? 0 multiply whatever is 0, right? Because everything is same, right? You set everything to 0, no matter you multiply 0. So every lottery will be 0. So everything is 0, satisfy what we said, right? Because everything is indifferent. Every lottery is indifferent. Fine, this is very trivial, of course. Now we got to something non-trivial. We have a 2-page of proof. First page and second page. The proof is not complicated. So let's go slowly, step by step, because I want you to understand the proof. Probably you might have learned the intermediate micro, but try to do it carefully here. So the proof is very simple. Now, again, as we said, we require continuity in the first step. Okay, this is continuity. We have the first better than the last one. So anything in the middle, AI, can be represented by mixing the best and the worst, right? And the probability is called alpha. Okay, and this alpha, of course, is unique because that is coming from monotonicity, right? You increase the probability of the more favorable one to get better, so better, right? And monotonicity comes from independence. Okay, but we didn't prove it, but you can check it out. Okay, you see what I'm saying, right? In that case, means that alpha, okay, depend on AI, okay, and this number is unique, right? So that's why we can write alpha equal to UAI. Is that clear? So that's by construction. So here you can see we construct the utility for each outcome by the probability that the best and the worst. So you can see the best outcome will be just 1, and the worst outcome will be just 0. Okay? So the best outcome is 1, the worst outcome 0. Anything in between, right, can be represented by probability over these 2 outcomes. Right? So that is why we have this guy. Okay? Now, and that means that I can write AI is lottery over A1 AN, right? Is that clear? Mm-hmm. So independence, okay, means that any simple lottery is mixing all outcomes of A1 AN, right? It's any outcome, right? Just combination, right? Reduction tells you P, right, is lottery over A1, A2, A3, AN. But AI is lottery over that. So you only care about the final outcome. That's what you have. Okay? Let me slow down here. Let me slow down here because that is something I think is a little bit complicated. Okay? So any lottery P, right, is lead to, you have n outcome, right? A1, A2, A3, AN, I'm not going to dot, right? And there's P1, right? P2, not going to, and PN, right? And A2, for example, right, can be written because of the continuity and monotonicity. You can written as A1 up to A2, AN, right? And this is UA2, right? And 1 minus UA2, right? That means that if I only care about final outcome, right? So I can just collect all the A1, right? Which is P1 times UA1 plus P2 times UA2, so on and so forth. So that is the last line means. Is that clear? Is that clear why the case? Okay? Every outcome can be represented by lottery over A1 over AN. Okay? Then you simplify by reduction, right? Compound lottery. is the simple lottery. Only have an outcome, right? Because only outcome A1 to AN. Is that clear? So the main thing is you build from there, right? You have to build up this one. Okay. So that's a key proof, keep the proof. Basically, you almost done the proof. So here, okay. I just need one more step, then I'm done. Okay, because remember, preferential lottery is the following. Okay, if we say lottery over 1 over 2, right? Because every lottery can be represented as 1 over n, right? A1 and AN, and then is lottery over 1 over n, right? Say, right? This is what we mean by lottery A over lottery B, right? And remember, monotonicity implies if I have higher probability of better outcome, I prefer the lottery better, right? So it means that they're the same, right? I just compare the first guy, and that's it, right? Is that clear? So that is the construction, why you would do that, okay? And before I give you a break, I just have one note that also you can see in Rubinstein textbook. What you can see, the axioms are very rational, very reasonable. Of course, you require a lot of computation. So that's why in Rubinstein idea, he said this expected utility theory, where people look at the outcome and weight it over utility, is what we call the normative approach. What we think people should do, rather than people were actually done. Okay, and in some sense, this is in most cases, look at the theory, is still okay. Of course, there are some cases that in reality that violate that, but in general, that is okay. So that's why we suggest when you do a modeling, you would do this first. If you get what you want, then stop. If you don't get what you want, simple, go ahead, pick up a more complicated theory. Okay, you would do this to build your model in the first round. If you don't satisfy, build a more complicated one. Same as what we have so far do in this course, right? We start with the standard perfect competition, oligopoly, monopoly, proposition, right? But there's no strategic interaction. There's no uncertainty in the beginning, right? We get increasingly more difficult, more complicated. And the reason is because if you can solve your problem without going to uncertainty, without going to game theory, why you do that? Don't complicate the model because if you can, right? The reason is if you complicate your model, actually your model is less generalizable, right? So that's why I said, because not use it because if you can. Try actually, if your model can be used, the less assumption actually even better. Don't overlook simplicity. Okay, if simple thing can do, don't do complicated thing. Okay, because I don't know whether you, but as I am a PhD student, I very tempted to use where can I find the most complicated theory to apply to my model. In fact, this is a wrong approach. Rather, you should try to figure out, is there any simple way to get what you want? The simpler the better, because the simpler you have less assumption, and means that when you do empirics, it's even better because less thing to check, easier to validate that. But anyway, I should end here with a break. We'll talk about that after the break. Let's have a break of 15 minutes. So in the meantime, as we do you reply so that you can leave your comment and tell me which part I don't explain carefully. I explain a little bit more. It's just a way to collect your response. 能填进就是有点问题可以点一下，知道吧？哦，对对对对，没有快改进的，而且还可以改对，看到这里对，我会看。新加坡已经会发一个人对吧？就是10来个习惯。哦。太热确实是。对。而且不是种子，真的往花东西走，最近国产的，肯定是放的西红柿。是我去新加坡吃了。我还以前有个同事上搬加拿大的，他一天17个，他说他们家的都也就是他们一天是关于的。有一天7个是多少？你看这一次来，人民币在这个一天7个，还是多的。时间他们这个是。其实我是坐在办公室后，我在写我的办公小报，有反击太好了，靠它一点消化非常快，所以说是要看消化，就消化太快就不消化，就 efficient 的，而且气的没有什么 efficient 的东西。没有吃那个意面，那你应该怎么做出来啊？对啊，马上来了。就是天天都坐在办公室，没办法，来吃再吃茶水。就是一方面。一天晚上学一定不吃碳水。晚上是不是会有罪恶感？你是典型的中国人。现在不仅就是说这个吸收是没有不好的，对，高速会升糖，这是血糖，对，就是跟米一样，应该他吃的还好，不应该他吃的早上没好，还有一天可以消化。如果是你的消化快，3、4个小时就。这很难啊。相比之下，我招太简单了。教程我们教复杂一点，让你了解它的那个，那个上面的话，它的这些， 对啊，我觉得很奇怪。So let's see if you have any comment because still confused about expected theorem. So that is normal because when I was a student like you, I was always confused. Let me close the door. So the idea of expected theorem says the following. So it simply means exactly this. Utility over log theory, okay, is basically come from your utility over all outcomes weighted by probability. Okay, that means the proof what we're trying to do, probably the question is not the theorem what it said, but what the proof is about. Let me talk a little bit once more. So what we're trying to do is try to say, okay, at the end, all the math behind try to say one thing, okay? After the first math is a probability over a lottery over n outcome, right? Can be represented by actually lottery over the best and the worst, right? And this actually due to monotonicity, right? Only one thing, right? So this means that the probability of higher the first number is better, okay? Actually, this first number is exactly expected utility, right? Of course, this is a function of the based on this, but we call it probability. We call it utility, right? So that's the idea, telling you that it's possible to do it. Okay. Basically, it's just like we need not tell us how probability and outcome interact, right? We isolate each outcome, look at deterministically, which we know how to do, right? In our topic 1, and just weighted by probability, and that's it. So everything become much easier, right? And it's linear. So very nice, right? So that's the idea. I hope I can answer your question. That's good. Let's see other question as well. So, today is cloudy. That's good. Yes. The key point, yes, that's a proof of expected utility theorem is one of the key of the proof, because we want to show you why we end up with expected utility, because we just use it in our daily life. In applying all the things, we tell you why this is true, and the reason why we need to know this true is because we want to know the alternative. An alternative involves of dropping some of the axioms there. Of course, we don't tell you how to do it, but this will be on our class. But at least we know why it's true, right? And that is the reason we learn Ph.D, right? We know why it's true, not just use it. Okay. Okay, most of you think it's appropriate speed. Yeah, you can still follow. Oh, so sorry, maybe is it too fast still? I thought it's not too fast, but you don't quite agree with. Introduce more detail about the theory. What I mean, explain the theory. Introduce more. So this is the idea of this is coming from Norman Morgenstern, and later we'll talk about this. The reason is because actually coming from St. Petersburg's paradox. We'll talk about that soon. But okay, so give you some more details. So let's go to that. So, but before we do, just let's step by step give you some more background. Okay. So the one of the first thing that you can imagine, right? Utility is a representation of the preference. So there are many equivalent utility representation of the same preference, right? Because remember utility, we said any monotonic transformation will do, right? You take a log, you take exponential, you take square. It's also all the thing works out, right? So here we have, because of the way that being done, okay? Actually now utility become cardinal. Okay? Before we have ordinal because any operation was done, but now we become cardinal, okay? In the sense that we only apply affine transformation, the linear transformation. You can just multiply and add, okay? You take log will be different. Okay, you cannot take square with different thing. Okay, so the shape of utility function is crucial. Okay, before you are linear, you have a concave and convex, make no difference. Okay. Now you can see the shape is different. That actually underlie later you will see the risk preference is depends on. Very important thing is the shape, the difference, and that is the key. Okay. So you can see this here already imply something. Okay. So, but we'll reserve it immediately later. But I hope that convey the message. Here is the shape of your differential matters. Okay. And we will proceed according to standard textbook. Okay. Talking about risk preference, and then later compare utility and talk about some applications. Okay. So to make our life easy, same as the textbook, we only consider one-dimensional uncertainty. Okay. Now we focus on the case of money outcome. So our action space is a subset of real number. I allow continuous, but as I said, everything from continuous continue to hold with some modification here and there. But anyway, assume that everything holds. So we can represent the outcome by a random variable L, lottery. Okay, it's a random variable. It's continuous, so I can have a CDF and a PDF, right? Big F and small f. I don't think I don't define that. I mean, it's a Ph.D. class, right? So everyone knows it. And that means that if I do continuous version, that means that I integrate over the U with respect to big F. If you're not happy with that, I mean, if you forget that that's just the integration guy, I can't write it. So it's just same as this guy. If you don't U of X, if you don't like taking this no different from this guy, okay? But just the integration becomes summation, okay? And that's the same thing, okay? And here the integration is a generic integration, right? It's not the standard one, so it include the discrete version, right? Probably many of you learned that as well, but not going to talk more, right? Because the general version of integration include the discrete guy, but we're not talking about measure theory or real analysis, but that's there, okay? And so by construction, it's very simple, right? We call expected value of the gamble, okay? It's just simply without looking at utility, right? Just U of X is just U, right? So this is expected value of gamble, okay? And we define a gamble is fair if the expected value is 0. Otherwise, if not, the fair is called unfair. Simple. Is that clear? So the fair gamble or the fair bet is crucial in our definition. Later you will see. Okay? This is very important definition because a lot of definition is behind this guy. Now, some of you ask what is the motivation or the background for expected utility. Actually comes from this very famous paradox. Probably everyone knows it. It's called St. Petersburg paradox. Okay, the gamble is very simple. It's a bet. Okay, where you will do the following. Okay, I toss a coin. Okay, if you head, you win $2. If tail, okay, I continue to toss a coin. Okay, if the second coin is a head, you get $4. Okay, if the second one is tail again, I toss again. Okay, you get $8. Okay, so every time, if I will give you 2 to the power k. If the kth one is head before the tail. Okay, so it's infinite, right? So you can see the expected utility. So expected value of this lottery is 2 to the power k and 1 over half of k, right? You multiply that. Every time it's just $1, right? Some of this is infinite, okay? The question in experiment, and actually, I think this is probably one of the earliest experiments that being done is because St. Petersburg, I think, is done by Bernoni family, right? no Benoni. I think they ask people around how much you want to pay for that, right? It's infinite money, right? How will you like to pay for that? How much you want to pay for that? The question is, okay? And he asked around, okay? Send letters. In those days, there's no WeChat group to send how much you want to pay, but he actually do the WeChat thing, send to the group, send all the mail to people, and people reply to him. Most of people would not pay more than $8. Okay, and you ask, wait a minute, it's infinite expected value, right? Why you would only $8? Okay, what's the reason? Okay, there are many ways to handle this thing. Actually, there's actually a lot of theory goes on to explain this. One of the theory we look at is called expected utility. Okay, and that means that how we solve this problem is your utility is not linear, in the sense that when you give you $1 billion to $100 billion, the marginal difference is very small, right? And that means that it's non-linear. So if we have something that is very big, this is also very, very small as well. But if non-linear, then that actually will converge somehow, right? So that is the idea. Okay, one of the ideas to do this is to make this non-linear, right? Make the money that you have is non-linear, right? Suppose the $1 billion, right? Give you $1, make no difference. If no money, $1 is very important. So some concavity on you actually help this converge, right? That's one way to do it, right? The second way to do it, you can imagine, is to focus on probability, right? As I said, there's probability weighting, right? You would do that, right? In case the probability is very small, right? Then you probably don't think it's possible, right? How likely, once you can easily do the Excel, right? Once you go beyond, how likely you get 10 times its tail or 100 times the tail? Almost none, right? Probably, if you think, probably at most you get 4 to 5 times, and that's it, right? Beyond that, you cut off, right? The probability is very small, you get to 0, right? So that's like some nonlinear process in your head, right? Because you never think about infinite. Right? I don't think anyone can have, normal people cannot think infinite, right? Probably you think up to 10 times already is done, right? Up to 10, and probably you just treat the rest as 0, right? And in that case, it's nonlinear, right? When it's nonlinear, there's something to do, okay? But we will not go that approach. We'll focus on nonlinear on the outcome, but not nonlinear in probability, okay? But as I said, if you do finance, you will do that, okay? But not finance, I rarely see people do that anyway, except you're doing some more crazy stuff, but otherwise not, okay? Is that clear? Is that clear why we do expected utility? Okay, it's one way to solve out this problem. Okay, and it has been worked very well, so we just based on, that's why we still use expected utility theory. It worked pretty well in many cases. Okay, of course there are many cases it doesn't work very well, but it's a good approximation. So because of this, let's define the following. Okay. We will call risk neutral, okay? If utility over lottery, okay, is same as your small utility, which is utility over your expected utility of the lottery, okay? What means is your utility over lottery is simply look at, you don't care about the uncertainty at all. You just care about expected value, one number, the average, and that is what you care. Okay, you simplify that. So it's a person who, okay, just look at the number, one number, right? You don't care about that. Okay, if you are risk neutral, which means that you're willing to pay infinite for the St. Peter's paradox, right? But I guess no people is risk neutral, but you will see a lot of paper is risk neutral, okay? Even in finance, I would say, because we read many theory there. They say, okay, because of tradability, we assume everything is risk neutral. Okay, because later you will see when things become risk averse, and then the model is not very tractable, become much more complicated. So it's okay to assume risk neutral, I guess, not a big deal. And if you look at a lot of paper that talk about firms can be risk neutral. Okay, and usually you can assume consumer and the firm. You can always you can usually easy to assume firm is risk neutral, and consumer is risk averse will be fine. Of course, it's usually the case everyone is risk averse, but it's okay to assume the guy, the bigger, more financial resources is more risk neutral. Okay, later we will explain why, what assumption behind, but that's the case. You can imagine the swell effect. Okay, and the reason is, one of the reason is because you are very rich, right? You ask Jack Ma or Bill Gates or ask very rich people, right? Are they willing to participate a fair con toast, right? If you win, you win $1,000. If you lose $1,000. I toast a fair con. Ask them, they don't really care. You ask me, I don't. Okay, maybe you do, but I don't, right? I'm very risk averse, right? Okay, because I have very low wealth, so as a teacher, so that is normal, right? So this is a proof. I'm not going to prove, but I think it's easy to read. But I will skip the proof. I mean, if you want to go further, you should understand the proof. But the idea is the following: if you're risk neutral, your utility, you can consider expected utility. Okay, whether your U is linear. Okay, what does that mean? It means that the following, right? If you linear means is Ux is X, right? So it means that if you face a lottery of 0.5 of winning $3, okay, and 0.5 of losing $3, okay? So the value of this lottery, okay, to you is just 0. Okay, and if I change it to the color, sorry, other one, L prime is 0.5 of $4, say, right? And 0.5 of negative $3, say, okay? Then my will be 0.5. Is that clear? Okay, I hope that is clear. So this can represent utility if you're risk neutral. And that makes calculation easy, you can see, right? Because life is simple, right? And this is why we do it in a lot of theory. Assume risk neutral. Okay? And later I will give you a very convenient way to handle risk averse, but I'll talk about that later. But is that okay here at the moment? Risk neutral. So is that okay? So this is the idea, okay? Consider lottery, give you 1 or 3 equal likely, okay? The expected value is 2, right? So if you're linear, then you actually don't care about give you 1 or 3 or 2. So that's why it's linear. This is a proof for that one, right? And the next one is risk averse, okay? Risk averse is saying that you are not happy to pay the fair bet, okay? You are well conservative, okay? That means that give you a lottery, okay, is not better than give you the expected value. Is that clear? That's the definition. So, and you can see when we buy insurance, that is risk averse. Why? Because insurance is not fair, right? It's not actually fair, right? You have to pay the risk premium or some padding to the insurance company, right? So you buy insurance is actually a risk aversion. It's a risk averse because it's not fair. But you are still going to do it. Okay. The idea, the proof will be saying that if risk averse, U is concave. Okay. So if you want to say expect utility and then you want the guy to be concave, okay, then they're the same thing. Okay, as long as this is the assumption. Okay, the concavity actually means the following, right? It means that the more money you have, the marginal utility is less, right? Because the marginal utility is the slope, right? The slope of getting extra dollar is getting less and less, right? So I think this makes a lot of sense for most of us, right? Is when you have, I can imagine, right? If I have 1 billion, right? Suppose, but never, right? Anyway, I get 1 million more would make me not very happy, not much different. From now, I give him 1 million, right? So that I think it makes sense, right? In many cases. So here is the idea, is the concavity here, right? Remember the example is either I have 1 and 3 equal likely, you give me 2, okay? And you have given a lottery, which is 1 and 3, right? The expected utility is here, right? So this is, if you ask me to do a lottery, whether you give me 1 or 3, okay? But I would rather have 2, right? If I have 2, then I'm much happier, rather than give me choose between 1 and 3, okay? So that is concave, okay? The proof is come from Jason inequality, if you're in probability theory, but I'm not going to talk about those, okay? But some of you ask me, okay, what is different my class compared to the things in econ department is they will do all this proof step by step, okay? And add more property when you see this and that, but I guess the main message for my class or the class will be similar, except we don't do some of the proofs, okay? Is that okay? Now that would be similar in the definition is, right? If you think a lottery more than expected value, right? That's risk loving. You don't want the certain one. And you go to casino, you buy lottery ticket, it's risk loving, right? You derive utility from paying the lottery, right? Less people think about that, right? And the idea is actually, if you think about this, is actually converse of this, right? Kind of like you get huge amount of money is giving you a lot of utility, right? At the very last, right? Maybe give you 1,000 would not that much, but later you give you 1,000 goes very big, right? It's a convex. So this is kind of the graph you expect, right? Is you are getting more greedier, okay, when you have more money. Okay, is it true? I don't know, but at least we can see that. Okay, and probably you would ask. Sometimes we see people buy insurance, we see people buy lottery. Okay, and how can we reconcile in this kind of framework, right? Are we having concave and convex utility, right? It's not consistent. How can we reconcile this fact? And some economists would explain in the following way: is if you look at a bet of big bet, we will be risk averse. Okay, that's insurance is covering big stuff. When you talk about small item, then you will be risk loving. Okay, you will buy lottery. Okay, so that's why it coexists, is because when people look at the things, their mind a little bit change. Okay, big thing is risk averse, big thing is risk loving, and that actually somehow kind of fit our evolution, right? When you imagine in the forest, dark forest, you try to hunt, right? You should be big risk. Let's say animal, the lion, the bear, there you should not go to fight, right? Although the return is very big, you shouldn't take the risk to fight that guy, because fight that guy, then you die, then you don't worth it, right? But when you try to pick up, say, the the tree over there, there's some apples, there's some risk, you should go and take it. Small risk. You should be brave for the small risk, but very scared for big risk. Okay, no, that's some kind of idea. Okay, but of course, this is, I mean, whether you take this is a reasonable recognition of the fact, I don't know. Of course, you can build a complicated model to do it, but that's one way to see how you apply. Okay. So now, from now on, we will assume people are risk averse. Okay, because that is actually explain most of our scenario. Okay, and lottery ticket is just very minor thing, right? Because I think in the world that is risk averse, the reason is the market, financial market, actually give benefit for taking risk, right? The risk premium is positive, right? It's actually you would be compensated for taking risk. Okay, okay. So that is what the word called risk premium. So that's why we observe this in the real world, risk premium positive. That's why it is. Okay, but we'll define what's risk premium. Risk premium is the following. Okay, so we will talk about your utility is so at the end is a wealth plus your lottery, right? Because depend on initial wealth as well, right? Because you know the shape is now important, so the initial wealth is important. Okay, and what we call absolute risk premium is your wealth, okay, plus this expected lottery minus this guy. But the reason is because if you're risk averse, this is bigger, right? So he's asking how much I can take away from you, okay? Given you you are doing the certain one, okay? So let's get back. It means that it means that if how much I can take away from you, so that you're indifferent. Okay? Imagine the fair bet. This is 0, right? This is 0. It's asking you rather take this lottery, or you can pay this to avoid taking lottery. Okay, that is what the statement means. Right? Of course, it's applied when it's not. You take the expected value. So let's look graphically at what it means. That will be easiest. And not there yet. Before I go to the graph, the other one is closely related to this one. Okay, it's called certainty equivalent. Okay, it's asking. I ask you to pay lottery. Okay, and what happens? Say no lottery. I just give you this wealth. Okay, and by construction, certainty equivalent is your wealth plus this minus this guy, right? It's actually the same number as you take a lottery, okay? So look at this graph, it will be very simple, okay? This graph will tell you everything. So initially, okay, you can choose the lottery, which gives you half of 1, half of 3, okay? Or you don't do lottery, it will be 2. Okay, so you will see, okay, if you take the lottery, you will be, this is your utility, right? Or 3 or 1, right? Half of it and half of it, this is your expected utility, okay? This is the number that you give to this lottery, okay? And if I give you the expected value of lottery, which is 2, right? Your risk averse, that's above that, right? This is the one that if I give you here, okay? But I'm asking is how much you are going to sacrifice, okay, in order to make you indifferent with the lottery, okay? Which means that I would be looking at the following, right? Looking at when I get the same utility here. Okay, so go down. It must be down, right? Because it's better to be certain, right? So you have to go down to here, to intersect. This is the one. I give you this. You take this the same as you take this in the lottery, right? And this, the difference, is called the premium. And this premium is all positive, right? And from this, why this is important, because this, no matter you use CAE or the Pi A, is actually coming from what? You, right? Risk premium is actually measuring you. And probably you ask why we care about this at all. There are two things. One is look at the financial market. Okay, you can the market come with the risk premium. You can calculate. How? Look at the standard thing is from finance. Probably people here would know. Is the risk premium is talk about equity risk premium, right? Look at the return of the stock over the return of the bond. And historical data tells you, I think it's more than 5% or above, right? And then can give us the estimate of U, right? That's one thing. The second thing is look at how you interact with the market, right? Given your U, right? You can tell me your risk premium, right? And then compare the market one, then you can see whether you buy this or not. Okay, there are two ways. Okay, but you can see this the reason why I look at risk premium. Okay, and you can imagine if your insurance company, that is the way you can charge. There's a profit margin of the insurance company, right? Because insurance company doesn't care to do lottery 2 or 1 or 3, right? That's actually the source of profit margin of insurance company, right? Because they can take risk. And that explains all the reason why we have Social Security, your pension with annuity, right? Because we don't talk about government in this class, but public economics will tell you, or environmental economics, right? Because the government is risk neutral, as so big, right? The wealth is so large, it's risk neutral, so we can take the risk. Right? Unemployment insurance, this is the thing, right? Of course, they can charge on behalf of you, right? But that's the idea. Is that clear? Right? Or why the bank can make money, right? Why don't you do peer-to-peer lending, right? Because take a lot of risk, right? As a bank, they don't care. So that's why they can charge interest, they can charge premium, because you are afraid of risk. But otherwise, why don't you just go and lend money to someone, right? Be a loan shark, a legal loan shark, right? Not illegal one, right? Right? You can do a legal loan shark, right? But you can't do that because you are risk averse, right? I hope that explains that's why we like risk aversion, because risk premium is what we observe in the real world, right? Not because we think people are risk averse, but because we actually observe things, right, in the market, and they're so prevalent that we don't assume that people are risk loving in most cases. Okay. And the other one is a little bit technical, but we still talk about that, but you will later see why we talk about this one. It's called the relative risk premium. Okay, it's a little bit technical, but people would think the risk in terms of percentage of their wealth rather than additive. Okay, so you would be thinking about your lottery is T times W. T is a random variable. Okay, it's a risk over the percentage risk, not absolute risk, right? Because before is W plus L, right? Your utility was over, but now it's TW. Is that clear? So the randomness not come from additive, but coming from volatile in terms of percentage. And you will later see why we do that, because in finance it's also very common. Later you will see, okay? But in that case, you can write, right? Your wealth is either this or T times W. This is the change of your wealth, right? And this is same, right? Will be this expected utility, and here the relative risk premium will be W times WR. Okay? And this is, we call, this guy is called relative risk premium definition. just definition, just nothing. I don't think there's anything in particular new here, but we call proportional risk premium, okay? It's proportional to your wealth, okay? How much wealth you are times the premium, right, will be your absolute amount that you're willing to accept, okay? And later we will define why it's important, okay? But this is just the definition. Nothing new there, but just if your risk is this, then this is how we define, okay? Just definition. So I'm not sure you need to understand or not, but this is the definition, just the formula. You will see why we do this very quickly, okay? Now, why we want to study risk premium, there are two things, okay? One is we want to decompose it into two parts. One is called the sub-objective component. It's called variance of the lottery, which is independent of how you think, right? Everyone would agree this is variance, right? The second one is risk preference, is how you feel whether you like to take the risk or not, right? So it's decomposed in two parts, right? And probably why you want to ask why you want to do that, okay? And this is important for finance, right? Or important in making decision, right? Because if you're government, you're risk neutral, this part should be gone, right? You only care about the variance, right? This part is more important, right? Of course, if you need risk neutral, we don't care variance anyway. This is zero, right? But that would be the case. Is we want to decompose it is because that can understand how the risk preference comes up, risk premium comes about, right? Because finance, right? Overall, at the end of the day, is looking at risk premium. I mean, especially asset pricing, right? Look at risk premium of different things, right? Comparing, and that is the reason we want to talk about that. Okay. Now, first we define what is variance, right? It's very simple. Right? It just this minus expected value square, right? Nothing new there, right? You learn undergrad, right? So now we will define this and we'll have a break, okay? So we will define that one is the variance is this subjective measure, okay? This one is later you will see, this one will be the subjective measure, okay? It's called Arrow-Peck risk aversion. It's invented by Kenneth Arrow, one of the founder of the modern economics. So he defined, and Pratt as well, the two guys. So they define it as the measure will be, as you expect, the numerator is where you expect, right? Because the curvature is important, right? If more concave, right? Actually, you require more risk aversion, right? If more linear, then it's more risk neutral, right? So that's why concavity. And the reason why it's negative because it's concave, right? Concave negative. So negative, negative, positive. So if you don't like negative, you just look absolute value, right? I just need the absolute value, right? And the reason why you need to divide it by the first derivative is because remember this utility is invariant to off-white transformation, right? Ux is same as A times U plus B, same thing. Let me repeat, right? Why we do that? After this, I'll break, right? Remember this thing. This and the same, right? I multiply A, the same thing. I forget about B, but multiply A the same, right? The same as B, right? So I wanted to compare utility, right? So it means that I don't want it multiply A the same, right? So that's why I need to divide it by this, so that utility amount I can compare. You give me two utility functions, right? And by calculating this, I can tell you which one is more risk averse, right? But you can simply actually means, right? Just this guy, but you divide it by that. Okay, of course you can say why this is a good measure. We'll show you very soon. But that is the goal. Another goal today is to show you this is a good measure. Okay, so let's break for 15 minutes and we'll come back. 其实可以啊，但是你们不可以啊，你们不一定可以。
你可以开着，对，上的人就以后自己看 recording， 对，就不用 make up
没有，其实 make up 就是 make up 成为把那个取消了，把它考试的那个，所以我觉得不行。虽然我觉得不行的话，但你们肯定很开心。
很开心。
是我们考试自己做的。
计算器只有用加参数，
我看着写啥？没看着我没打字还是？
我就知道。那个谁，我不看，没有，我一定去看。我喜欢他看的，我喜欢你左右的两位，最喜欢你们看的，而且很 obvious 一个是唯一开始，对，绝对有个人很冷漠。来的是太妹吗？然后
没两个。
那我打起来是我一个朋友记得，特别是他也喜欢这个。那他可能就是会喜欢。我 我团不起一点儿。我可能已经有一个了，还有一个奇怪的是有一个结婚还要办。那不会。是呀。
都应该都有。
对啊，那我不知道他说的对还是什么了。那不好，上次有一个一起挨骂。为什么办婚礼不好？小菜会来的，而且他就已经是。然后那次会有。哎呦，我银行卡有。现在的专辑是怎么样？就是还是书本儿。没有，可能我们熟。
我跟你讲，我是 business person。
我也是，就都不要投，接受不了一点风险。Insurance。
我觉得你反那些个比较多。
大家都觉得我比较多。上课老师都说啊，我们都不投股票。最后他这个很可怕，说他之前火过，然后也亏了。对，他才说如果我能赚钱的话，我就不在这里做事了。
纳税了。
你懂得越多，你怕的越多。
懂的都有怕。
对啊。懂越多越知道自己其实根本就没有办法理解。
但是 EMH 的话就不会懂这个。EMH 比例分。其实两个地方都不是，都很接近，但是你是有 99% 你是选的是1%有个 smart enough 的地方，但是我不觉得我是 smart enough 的人，就没有办法。
是啊。但我发现我可以拍照也应该有人来带这样。所以对，现在已经结婚了，就是可能要看过量。但刚开始做完就觉得哎新鲜。大家说他的头是好好抓，因为他很容易抓他的那个头发。
Maybe we should resume. The idea to repeat is that we have absolute risk aversion. It's trying to measure the curvature of the utility function. And the reason we divide by the first derivative is because of the fact that any affine transformation would give you the same utility. So you have to divide to make sure that I give you any utility function, anything you multiply should give you the same thing, right? That's the reason. Okay. And as we said, we want to do decomposition, okay? And that's what it means. It turns out that we can solve, probably we skip the proof, I guess, because I think we save the time to do better. More important thing is to show you that the absolute risk preference actually can be decomposed in two components. One is the variance, actually variance over 2, but then it's just variance. Because 2 over 2 is just normalization, right? Just variance. And the second one will be just relative risk absolute risk aversion, right? So it means that if you have a larger variance, right, then your premium is larger, right? And you're more risk averse, then you require more premium. So why we want to decompose it, as I said, I mean, that would be useful for empirical understanding, right? And then you want to check out which component is what, okay? And I'm not going to prove, but you can see the proof is just basically do Taylor series approximation to second degree and then just do it. Okay, I want to say proof, I would say that's calculation. But I guess I don't want to go over that unless you have a question, but you should be able to read that because it's nothing very deep thing. Okay, if you want, you can go over that, but just very standard thing to do it. Okay, so here the reason why I want to talk about this is because absolute risk aversion is because of, in practice, we want to model uncertainty. This is the function we use, one of. We'll talk about two functions. This is one of the functions, right? Just like when we talk about topic 1, we talk about utility. We talk about perfect substitute, ux12, right, is x1 plus x2. The other one is complement, right, minimum of the two. The third one is like Cobb-Douglas, right? The third one is like CES, but these are 4 the things you build your model, and this is most common. Right? Same for potential function. You have the same thing. You have a Leontief, you have a linear, you also have a Cobb-Douglas, you also have CES. Right? And uncertainty, there are 2. Okay, this is the first one. Right? It's constant absolute risk aversion. Is like this style. Okay, and I'm not going to do the proof, but you can see that here is this is equal to B constant. So that would be the function. Of course, usually you ignore the C anyway, right? C is just basically useless, right? And often type A is also gone, right? B also gone. So usually you can see this is the guy usually you see, right? This is the guy that you would do your problem, right? So you assume the agent like this, and then you're done, right? That's how you do the modeling, okay? And of course, this is not the most common one, but this is the one that you can use and make your life easier. And you will see why this is true is you assume that people who have constant risk absolution, right? You just ask, no matter what your wealth is, right? This one is independent wealth, right? And you ask them to take a fair bet, right? And what's the risk premium going to give? It's always proportional to its variance, because constant, right? So it means the following, right? It means go back to here. It means that your risk premium, it just this RA is constant B, right? So it's basically as long as fair bet, it's just proportional to B times the variance. Very simple, right? You can imagine if I follow this, my calculation is easy, right? I look at the situation, I look at how he liked this lottery, I just look at his expected value, okay, and plus this risk premium, right? I can calculate the result fairly quickly, right? So that is the reason why you want to use that. Is that clear? Okay, and this is one of the main goal, right, of this class is to tell you this utility function and give the foundation for that. Okay? Is that okay? Is that clear? I mean, of course, you don't really care about expected utility everything, right? Because at the end, this is the calculation required, right? Of course, that one is just give you a foundation why this works. Okay? Oh, sorry, I should not say too much okay, right? Someone told me. But okay, just try to see whether you're okay or not. But I say, is that okay? No, I don't know. So this one is about relative risk aversion. As I mentioned, is people would talk about the risk in terms of percentage of the wealth. Okay, the same risk, but you consider uncertainty model as a percentage of the wealth. And in that case, we would define. Okay, you can see the proof. Probably you don't care about the proof, but there's a measure, okay, relative to the wealth. Okay, there's a proof there. And the proof is, again, it just, you define the utility as a function of t, you just care about, okay? And then you take the same measure, turn out you get this guy, okay? And why this is important, like you will see, is we can define the relative risk premium, which we define. Again, the same thing. Multiplication of variance and the relative risk aversion. Okay? And of course, this is a decomposition of subjective and objective component, but the main part is this one. Okay? This blue one is the thing that I want to convey mainly. That the before is just the building foundation block. The idea is we assume constant relative risk aversion, which is usually you see in finance paper, and also we see many paper that you see in business journal and even econ journal. Is we see log utility, right? Those who take finance, to take macro, you see that often, right? Or the CES style, like that, right? And what is the constant means, right? Because you take the same, you take the RA is this is B, this is 1, right? That means that you have constant. It doesn't depend on how much you have, right? As long as my bet is talking about 50% of my wealth, okay, then I always attach the same risk premium, right? It's just proportional to the variance, right? So whether it's the same, I don't know. But if you think this is very rational, right? You ask me and ask B.B.A. You ask me, do we have the same risk preference? Probably not. But if you ask our risk preference in terms of we are betting in terms of percentage of our wealth, I think we are very similar, I guess, right? If you bet 1% of his wealth, I bet 1% of my wealth, I think would not be too much different. Okay? If you take this as a right assumption, that is the formula. And that's why in finance you see often this. right? Because this is, I think it's very natural, right? Because the CAAR, right? That one is assuming no matter how the wealth you are, you would think 1 billion bad, same no matter how wealthy you are, right? But here just like if you take the bad in some percentage, you're the same, right? And this is, I mean, of course, usually you take A is 1, C is 0, right? You take log, okay? So that's the simplest thing you can imagine, okay? So suppose you apply it to your work, this is good. Or you can take, sometimes you can take the other one that's common, this one, right? You can take a square root of x, right? Take a square root. Because b can be 1/2, right? So take a square root, it's also common. So these are to give you foundation, and usually you take this form, right? This is the CS style, and you often see in all the macro, IO, a lot of model like this one. Okay, so that's I hope this gives you a foundation why it's good, right? Because at the end of the day, this is the thing we use, right? And I give you why they're true, and you can understand why they're not true, right? Is that okay? Is that okay? Is there any? Do you have any question? Okay, I don't say okay. Do you have any question? You have a question? Do you have any question? If no, then okay. We will talk a little bit more about compare lottery. Okay, and we compare able to tell look at this lottery, right? Comparing different people how they make decisions. We can tell them how their risk attitude, risk averse, risk loving, and we want to talk about compare lottery. Okay, the first thing is what we call stochastic dominance. Okay, we want to say a general comparison that a comparison lottery that hold for a general case. Okay, so the idea of this is the first one is called FOSD, first order stochastic dominance, which says regardless of your risk attitude, okay, you would prefer one lottery over the others. Okay, then it means that you always take the one that is not dominated. Okay, so this one is this is actually the definition, right? You would look at lottery F and lottery G, right? F is better than G if there's always whole. Okay, and this is the definition, and turn out that this is equivalent to saying that the CDF of the better one is always less than the worst one. Okay, so that's a proof. We're not going to prove it, but this is a very important proof. Okay, and that is very simple. It means that if I know the lottery, the CDF, which is the description of the lottery, right? So it's, as long as I know the CDF is lower for whatever value, then it's always best. Okay? And look at the graph. I mean, this is not very intuitive. Look at this graph. You can tell me F is better than G. Why? Look at every vertical line. Okay, how you do it. Look at every vertical line, like the green one. Is it F below G? If so, F is better than G. The reason is very simple. I'm not going to do the proof. You can look at the textbook. The proof is not very difficult, but I don't want to spend my time on that. But you can imagine, right? This is money, right? So that means that if everywhere is lower than that, right? That means more money is there, right? As long as you prefer more money than less money, then that's it, right? That is coming from monotonicity, right? So, because regardless of risk preference, right? You satisfy monotonicity, right? More money better than less. So that's a proof, right? No matter whether you risk loving, you risk averse, doesn't really matter. Is that clear? Of course, you can prove. You can do the proof quickly, but I'm not going to do that. Is that clear? Is that okay? Now, of course, you can see the FOSD is very strong. That means that most of the thing doesn't apply, right? Most of the cases, FOSD would not tell you anything because, I mean, you can imagine that simply, you can imagine the scenario. Let's see the scenario, right? If I have another one, let's call this one. Say, suppose I have this, K, okay? You can't tell whether F better or K better. Although in your mind, then you would tend to think K is better, right? K should be better than F, but just for somewhere small range, right? K is not as good, but you can't really tell. And usually there's some intersection, then you're done. You cannot say anything, right? It's not that easy, okay? So how can we do about that, okay? So it's the way to do in economists, we call second order. Of course, why it's called second, but just people think this is second order, is we only focus on risk-averse agent, or risk neutral is also okay. So we forget about risk loving because risk loving is not important. So we just reduce the domain because we're difficult to satisfy, right, for all decision maker. So we just reduce the set, right, to the case where we only care about risk averse and risk neutral, okay? And we want to compare lottery, just do that, okay? So if you focus on risk neutral, okay, and we will call it F and G, they have the same mean, okay, same mean. And we will call it SOSD if, okay, no matter your risk preference, as long as you're concave, F is better than G. Okay, we only restrict to ourselves. First thing is they have same mean first. If a different mean, then it's very difficult to say. Okay, I don't compare just like the finance, right? Risk and return. I just focus on the same mean first. Okay, and then I look at, I want this lottery better than this. Okay, for every risk preference, as long as they are risk averse. Okay, can I do this comparison? Okay, is that clear what you're doing? Okay, let me repeat the statement. Is I have two lottery, they have same mean. Okay, if for every people who is risk averse or risk neutral, who think F is better than G, then I will call F is SOSD G. Is that clear? Yeah. If that's the case, we can simplify, turn out to be another simplification. This very important theorem. Of course, we omit the proof. I'm sorry about that, but you go to the econ department, they will tell you the proof. But the proof is not difficult, I'm saying, but we don't have time, unfortunately. So the answer is very simple. The proof is just the integration. Okay, looking at the height, but looking at up to that point, the area. Let's see the graph. It's very simple. So I look at particular point. Okay, look at the area on the left-hand side of G and F. If F area less than G area, F is better, no matter your risk preference, as long as it's risk averse. Okay, let me state again. FOSD is look at every single point. Is it F less than G? Very demanding. But now we are not looking at every single point. Okay, we look at every single point. Look at backward. Integrate the area. If the area is less, then it will be better, regardless of your risk preference. Is that okay? And so the last one, I think, is the most useful one, which is another way to describe, okay? And usually you want to order it because this actually, the FOSD, SOSD is the way that you try to test your model prediction. okay, is look at the lottery, okay? I have F, okay, which follow this one F, okay? And I have a mean zero random variable, it's a noise or error, okay? Expected value 0, okay? And I consider instead of y is x plus epsilon, it's very common in finance, so accounting is like signal, right? You don't observe the thing, you observe the thing with some signal. That's very common. Okay? This is the standard, I mean, I would say a lot of models is like this, right? Because you don't perfectly observe what you see, you have some noisy signal, right? And people will call G is mean preserving spread, okay? It's the same mean, but spread out, okay? And if it's mean preference spread, then of course it's bigger, right? So the not spread one is better than non-spread one. Okay, of course the original one is better, right? Yeah, noise is worse off. You prefer the original rather than the noisy one. Is that clear, right? You prefer the lottery that is without any noise component. Okay, and why this is important? Because this is usually how you do a modeling, right? Because you would be adding a signal there, okay? And is that okay? I talk about this because if you go to seminar or read paper, they just directly told you, okay? We will look at, say, usually compare statics, how you do in probability framework, right? Because you can easily imagine it's deterministic, right? You can model the environment, just a parameter increase, right? And how can you increase uncertainty? It's not easy to model parameter easily, right? Because even though you assume normal distribution, are you increasing the mean or are you increasing the variance, right? So, and this tells you that this is the way to do comparison, right? You can imagine your model, people behave in this way, right? You can calculate all the thing. You can consider under and uncertainty, which is SOSD, then look at how people behave differently, right? So this is usually how you try to characterize comparative statistics in more general way, right? Because you can always assume epsilon is normal, then you can do all the calculation, right? But if you want more generic, right? You don't want to make any assumption there, that is the way to do it. You want to do a quantitative comparison, this is the thing. But that being said, I mean, not very useful, so there's some usefulness, but if you theory paper, then you will see them. But in application, probably I guess most of you will not need them. So that's why I skip all the proof, because I said, I mean, I just do the proof that I think is useful. Okay. Now here is, I think, this useful one, because especially people here in finance, is what we call mean variance analysis. And I will spend more time on that because that is the thing that probably that is what you do. Okay. And in reality, we can probably know the mean and variance of the lottery very well. The skewness, kurtosis, those kind of high order, we don't know very well. Okay, and mean and variance, and it will be easier if actually our model can deliver the agent only care about mean and variance. Okay, and we try to, and actually a lot of models assume that. Okay, and here we give you foundation, or under what condition, actually only care about mean and variance. So that's the idea. Okay. So there were two cases. Of course, they are very limited, but that is what we can do. And beyond that, it's very difficult to do. So there's two assumptions. The first one is called contracted utility, which I think is very natural. But you can add C here, there's no difference. Right? And I see the constant C, there's no difference. But it's just like your utility is depend on contracted. And you understand why B is negative, because concave. Right? And the other one that is called the constant absolute risk aversion, right? And plus lottery equal follow the normal. But I will go this one a little bit slower because I think it's the most important thing because you apply in your actual practice. Okay. So let's make the formal statement here is if your utility is contracted, okay, then every lottery with the same mean and variance, the same. What do they mean by that? It means that lottery A, lottery B, they have same mean, same variance. I don't care about kurtosis, skewness, whatever. Higher degree the same. No different. Only the utility. For me, I look at this lottery. Tell me the mean, tell me the variance, done. I can tell you how much I like it. Okay? So I don't need to worry about higher order thing. Okay? So that means very simple, right? You can just write your utility in this form, right? And that is your model easier. Okay? Or you can simply write your utility based on mean and variance. Okay? Which you will see later as well. But okay. I'll go to this proof because I think we should, because it's not difficult. Okay. So consider your wealth is W and lottery is L, right? Your utility over the lottery is expected utility, right? Is expected this one minus expected that one, right? And you can expect expectation, you can take inside, right? Square, you can square that, okay? And then you can take the expectation inside, okay? And you can see only mean and variance, okay? So there's nothing beside mean and variance. So there's no higher order, okay? So that's why it holds, and that's why you can see a lot of paper just simply say, okay, assume the guy is contracted utility, and that's it. And let's go on, care about mean and variance. Okay? You will just see that the paper just, okay, start and skip. Okay? Is that clear? So, is that okay? Now, the next one, I think is way more common in the finances. You have the exponential utility, as I mentioned, right? And R is the measure of the absolute risk aversion, right? And if you assume lottery, actually the stock price or stock return is normal, right? Turn out that your utility only depends on, probably can forget about the wealth, right? Would be the mu minus, should be, I missed the R, okay. I missed the R there. So there should be R. Okay. It depends on this, okay. I go to the proof of this one because I think it's important, because the reason why I want to focus on this is because you will see a lot of paper that they just do that. Maximize mu minus R sigma square. Or whether 1/2 or not. You will often see this thing happen. Maximize mean minus risk aversion. This is the way they do, okay? Because they just basically skip, okay? And of course, underlying is saying that they are talking about this thing happen, right? I mean, this is try to demystify why they can do this, right? Of course, if you assume contracted utility, in some sense, this is also okay, right? But this is the most direct one, okay? It's the foundation. I guess this is the one of the most important part we want to convey. Is that okay? So I would go to the proof slightly slower, okay? But I don't want to go too much. But it's a normal distribution, the PDF. And explicitly just take this, okay? Just plug that in, right? And this is what you have, okay? Just because the E, the good thing is you can combine, okay? You can check the calculation. And what you do is you try to take out the component that's unrelated to this, okay? And this guy is 1. And turn out to be is E to this guy. And R can take out a constant, right? So basically you care about this guy. So that's why you can go step by step. It's not difficult, but some algebra, just care about this guy. So that's why you will see a lot of paper just strictly go to this guy, assuming you know all the calculation. Okay, this gives you foundation, because I think this is most important, because when you read paper, you don't say, wait a minute, why just maximize this guy and then you're done, right? And for no reason, they say, oh, either they're contracted utility or they assume Cara with normal, that's the reason. Okay, and they assume you know it, they don't give you the derivation. I mean, when I read paper, I say, okay, what happened? But now I give you why. I think that's the most important. Is that okay? I guess you don't need me to go step by step, right? I think it should be fine. Okay. The proof is, I already tell you how to prove it, but I'll just skip a little bit. Is that okay? Is that okay? So now I would like to finally last 10 minutes, okay? Give you some application, okay? Not very complicated, but there's something interesting to talk about, because based on what we have, okay? I will do very quickly, because it's not something, you learn it in undergrad anyway, if you have done anything. So probably in finance, right, people know, even if you know probability, know you want to diversify, right? Don't want to put all the eggs in the same basket, right? And you can imagine that why they do it, because you put it in the same basket, right? It's being SOSD, right? So diversification is basically second order stochastic dominance idea, right? So regardless of risk preference, you want to diversify. So that's the proof. I'm done. Okay, this is just more detail, but the idea is SOSD imply we approve it. That's why you want to diversify. Of course, if you're risk loving, then probably you want to diversify, right? But if you're risk averse, then SOSD imply you want to diversify. So first thing, I mean, this is just some proof there, but I don't think it is matter. The second one is called contingent commodity, or what we call the influence idea. Okay, they're the same idea, but I just go very quickly, because it's only important in the sense that it's very important, but it do explain something. So let's go quickly on this one. You consider the world only have two states of the world, good or bad. Okay, good is pi, bad is 1 minus pi. Initial wave is W. Okay, and you can imagine that the state of the world, each state of the world is different good. Okay, maybe umbrella during raining or umbrella no raining. Okay, and they are two goods. Okay, the question is the two good or different. Okay, how and the price also different. Okay, you can imagine that there's a market there that trade this kind of contingent commodity, right? You can just imagine there's a market that trade when the rain is there, there's umbrella sell this price. When the no rain, umbrella sell this price. Okay, there exists this kind of market. Okay, in that case, so expected utility, right, will be pi times WG. Yeah, how many you have, right, and how many you have in the that time, right, and this budget constraint, right, and the idea that, remember when we learn topic 1, right, how much you want to buy if this market exists depend on MRS, right, the price, the internal exchange rate and the external exchange rate are the same, right? So MRS would be same as the price ratio, right? And if the market is competitive or fair, the price should be same as the odd ratio, right? Because there's someone who are willing to trade. And if you look at combine this to this one, right? That means that these are the same, right? And because U is concave, that means that you would make sure that they're the same. Okay? So it does explain that you want that regardless of the state of the world, you want to make sure that you receive the same utility, right? And that explains why, somewhat, you don't see things like umbrella in the raining time, umbrella in the sunny time. There's no contingency being sold. So if this doesn't hold, you should expect financial market will be much more complicated, right? You should expect dividend in the good time, dividend in bad time will be different. You have a more comprehensive thing. But people tend to want to make certainty because they don't want uncertain, right? So want to make sure that regardless of the case, the same, right? So that is the reason why when you get married, if you get to marry, so what is the off there, right? Is regardless of your partner is healthy, rich, poor, unhealthy, mean the same. Why? Reduce uncertainty, right? You want to, regardless of what happened, you want the same, right? You don't want to say, okay, if you got cancer, we are going to divorce. If you get rich, I'm do what? You don't do that, right? You make sure that no matter what, same. Right? Somehow it's just like reduce uncertainty. Okay? And I'm not going to detail the proof is same. It's saying that if you can buy insurance, actually the same math here. If the insurance market is perfect competitive, okay, you can check the proof. I'm not going to go detail this one because the same proof. You would be showing that if you're risk averse, you would buy full insurance. So if you are going to cover everything there, you try to make sure that regardless of scenario, whether maybe I just go over the setup. Okay, setup is very simple. So they have setup is here. The initial wealth is W, loss is L, probably P pi. So either you have no accident, you got W, accident you minus L. Then you have you can offer premium P, okay, and you can buy your coverage from C to L, okay. So this is if you buy Q, this is your payoff, and you choose the Q to maximize your utility, and as long as it's fair, P is equal to pi, and it will show you that you would buy as much such that regardless of accident or not, the same. Okay, so they will buy full insurance. Okay, and that is what it tried to mean, and it just means that explains why insurance company exists and they earn a lot of profit. The first is insurance company is risk neutral, okay, and you're risk averse, right? So you would willing to pay the risk premium, right? And you would buy in full, right, if possible. Okay, so that explains that. Okay, not going to go to detail, but same as what the fund manager idea, right? The fund is the same, right? Fund is diversify the risk, right? Fund is actually pulling the risk, so that's why you need to pay for them, and then they reduce the risk for you. Okay, not going into detail, but I guess the last a few minutes I want to talk about this one. Okay? For those who do finance, they will know very well, but for those who don't, then I think it's interesting. So here is what happened when you go beyond expected utility theory, because what we have is utility of the certain outcome and take probability, just that's it, right? And as I said, it doesn't fit some of the scenario. And what is there are many competitors for expected utility theory, and the one that is most promising, at least in finance and many applications, is called prospect theory. So I'll just detail a little bit about what it is. First is called reference dependence. Reference dependence means that you are not evaluating absolute wealth. We are going to what the final wealth we have, right? Because what we have utility of W plus X, right? But what the reference dependent means is win and loss. You look at where you are now and look at win and loss. And win and loss are treated differently. Okay? So here we call the loss aversion. Okay? So what it means is the following. Instead of looking at this utility like this, okay, what you're doing is look at where you are. You just look at X. Okay? And you will be, when you look at gain, you will be risk averse. If you lose, looks like this kind of stuff. Okay, it's like convex. Okay, it's look like this. So it very well explains why you would be lottery is like this, right? So that's why you want to pay lottery. This is the idea. So this is the standard graph. I think by and the probability rating I already mentioned that, right? Overweight, low probability, and this is the one I mentioned, right? This is P equal to X, right? And there's this, right? The probability, right? You underweight, high probability, overweight, low probability, right? So that also explains why you buy lottery, right? Lottery is low probability, but you overweight it. So these three are very useful, at least in terms of empirical or in terms of modern application. But one of the big problems is they are not very treatable. Okay? Means when you apply to the model, then you can't really solve many of stuff. Okay? In pencil and paper, right? Even Mathematica cannot solve it. There's no closed form. But still, you can derive, if you are good in math, you can derive certain things. But that's why I don't talk about that, because if you can do that, then you don't need our class, right? At least at this moment, okay? So what is the application of this prospect fee in finance, okay? That explains why skewness is important, right? Because that explains actually why you see a lot of people want to buy for star stock like Google, Tesla, or GME, they increase, or Bitcoin, right? They expect they increase a lot, can be, okay? It's a positive skew, right? And how can you explain that? Is you have to kind of weight it, or you think in terms of like this, right? And that would be very useful. But for most of useful application, I think the expected utility is you're done. Okay? But recently getting more and more common, you have prospect fee theory. Okay. I hope okay. So I overrun by 1 minute, but I hope it's fine. So I will see you next week. Enjoy. By the way, I will upload the assignment to the Blackboard. Will be basically 2 questions. 1 question for the equilibrium and 1 question for result version. You have 2 weeks to do it.